let's go into the Smith chart. Now, I want to point out here on this thing that when you turn the Smith chart upside down, I had a college course. I had an entire semester, by the way, on the Smith chart. So I'm just going to cover various, just the surface of what the Smith chart actually is. But my professor considered Linville to be a Smith to be a plagiarist. And he claimed in his course that it was a guy by the name of Linville that actually calculated all these lines in here. And by the way, that's what my college course was. I had to calculate every one of the locus of every one of these damn lines, and ad nauseum. You turn the two upside down, this becomes what they call an admittance chart. My professor never, ever once in the entire course called it a Smith chart. It was always a Linville chart because that plagiarizer Smith. Everybody else in the world, of course, calls it a Smith chart, and that's what we're going to do. Just a little side humor, perhaps. But now, remember the chart that I showed you before? On some printed Smith charts, you'll see this stuff on the bottom, and it's really just the same chart. You draw a line from the origin all the way down here. That's 1-to-1 SWR. It's infinite return loss and so on. It's really the same thing. You can get your SWR, you can get your gamma, you can get your return loss, all from this chart. And it's nothing magical. It's just a different way of drawing a chart. So remember what we talked about the complex plane again, where we had a resistor in series with an inductor, and it appears as a point on the XY plane, if you will. And likewise, below the line, we have capacitance. So above the line, we have inductive reactance, as we call it. And below the line, we have capacitive reactance, as we call it. Over here to the left implies negative resistance, which implies amplification. We're only going to be talking about the right-hand plane here. So this is all passive networks over on this side of the plane. But when we get to the Smith chart, it is really, I wanted to point out that one of the problems with representing it this way is that you're not seeing all impedances. All the off the chart over in this area, you're not seeing it because they're too large. And likewise, at the top and the bottom, as you approach infinite impedances, they're too large and you can't represent them on one chart. What the Smith chart attempts to do, it represents all impedances from 0 to infinity, all on one chart. And that's why everything kind of gets curved and so on. But essentially, the Smith chart is the same kind of thing. The horizontal line here is just the pure resistance like we had on the other chart. This represents pure resistance, and it's calibrated at 1.0 at the center, 0.8 and 1.2, 1.4. I'll get into that in a second. But above the line, just like in the other chart, all impedances above the line are inductive reactances. And I'll tell you how to read all of this, because you can just read what the thing is right off the scale. But everything below the line are capacitive reactances. So this point represents a resistor in series with a capacitor. This point represents a resistor in series with an inductor. Excuse me a second. Get a corona cough out of the way. And yeah, so I guess that covers that. But anyway, so what we have here, and we want to zoom in at the center point on your Smith chart, and I'm talking about a printed Smith chart because you don't have these scales on your VNA, but it's important to understand what they represent. But at the center of all Smith charts, you'll see the scale starts at 1. And this represents the normalized impedance of 1 ohm. So these circles that go this way, all these concentric circles are called constant resistance circles. And they're called that because they intersect the resistance line at a particular point. In this case, it intersects it at 1 ohm. And anything along this line is 1 ohm in series with some inductive reactance. In anything below the line is 1 ohm in series with capacitive reactance. And again, as I showed in the previous slide, anything above is inductive, anything below is capacitive. And it's really that simple. Now, we can take our 1 ohm resistor and go this way. Let's just add an inductor in series with it, and we can read it off. At this point, we have 1 ohm in series with 0.2 ohms of inductive reactance, and that's our point that I kind of showed above the line here. So we can go over here and see 0.7 ohms in series with 0.4. We can have 1 ohm in series with minus 0.2. And this is basically, it's just a scale the same way the other graph was. And it's an impedance plot. And the people who teach Smith charts will say, oh, it's not an impedance plot. It's actually a plot of the infinite gamma curve, gamma space. Well, remember, gamma is the reflection constant coefficient. Gamma is resistance and inductance. It's impedance. It's all of the same stuff. So don't buy into that. It's an impedance plot is the way to take a look at it. It's the easy way to consider it. Now, because we don't deal with numbers like 1 and 0.2, we can make this center point to be anything we want. And in your VNA, the center point is 50 ohms. And I'll show you why they chose that in a minute, because it has to do with transmission lines again and Viswar circles. So we go into this pure resistance point of 1 right here at the center of your chart, and we're going to just multiply it by 50. We're going to represent this to be 50 ohms. And every number out here has to get multiplied by 50 now. And this process is called normalization. Your VNA does this automatically. The big boy machines can have different numbers, but your VNA only works with 50 ohm systems. Yeah, that's the price you pay. You want to do some 70 ohm work, pay the 50 grand, and you got it. So moving on here again. So this center point now is now 50 ohms, which makes this point 0.4 times 50, or 20 ohms. This is the resistance circle now. So this now represents 20 ohms. And this point, which is 0.2 times 50, is 25. So this point represents 20 plus 25 plus J25. If we come down here, likewise, having a series capacitor, where this is 0.6, this point is, since it's on the 50 ohm constant resistance circle, it's now 50 ohms minus J30. So you can, just from the chart, if you have a real chart, you can look at the impedance and just read it directly off the chart. Now you'll notice that that some of these lines end. They don't really end. They actually go all the way down asymptotically down to the origin. They're just eliminated here for clarity. You can imagine how cluttered this chart would be if they didn't cut some of these lines apart, because they would get really crowded down in here and you wouldn't be able to read them. But the 0.5 line actually is continued all the way in. You can kind of figure that out. If you need better clarity, you need to renormalize so that you can read it better, but I'm not going to get into that. So here's a summary of what this was. Remember, here's our circles of constant resistance, because they intersect the line here. Here's our arcs of constant reactance. This is an inductance line. This is a capacitance line. Now, an interesting thing is that because we've normalized this to 50 ohms, we can draw some constant SWR circles. These do not appear on your Smith chart. They never appear on a Smith chart. So you got to take a compass, and that's not the thing you use in the North Woods. It's the thing that with a little point on one end and a lead on the other, and you draw circles with it. But you can start drawing circles of constant SWR around the 50 ohm point. So remember our example over here of 25 and 100 ohms? A 2-to-1 SWR circle intersects at 25 and 100 ohms, but it also is all these impedances all the way around, both capacitive and inductive, all infinite number of points on this circle will give you 2-to-1 SWR. Likewise, you can draw a 5-to-1 SWR circle. You can draw a 1.1-to-1 SWR circle. And as you increase the length of your transmission line, you are traveling around. Where's my pointer now? There we go. You're traveling around this circle. You travel over. If you're increasing the length of the line, you're traveling around clockwise. If you're decreasing, you're traveling around counterclockwise. So what does this mean? Let's say we had an antenna out here that had 25 ohms pure resistance instead of the 50, okay? If we were to take a transmission line now and add it in, and let's travel around our Viswire circle until we hit the 100 ohm point, this is a quarter wavelength of travel. One full rotation is equivalent to a full half wavelength. So half a rotation gets us to the 100 ohm point. That is taking a quarter wavelength of transmission line, and you're actually transforming the 25 ohms. Even though you have 25 ohms at your antenna, you will measure 100 ohms at the input of your cable. And likewise, if you continue going on, you will get back at a half wavelength. You'll return back to the point where you started. Every half wavelength that repeats, every quarter wavelength, it sort of inverts. So again, when we looked at this formula before, there were 2 points with that intersection, but it actually is an infinite number of points on the SWR circle. So if you were to take your 25 ohm line and you added a little bit of coax, and you'll see the wavelengths on here. It's not shown on this, but it is shown on the actual Smith chart. See if I can bring that up and you can see it. In the fine print over here, it says wavelengths toward generator, wavelengths toward load. And you can actually say, okay, I'm going to add 30 degrees of wavelength to it, and I can follow the constant Viswire circle and find out what that impedance is going to end up. Get back to this one. So now here's the cool thing, and the reason you probably don't want to use the Smith chart, okay? It's an interesting thing. And here's a screenshot of a VNA, one of these inexpensive VNAs that is sweeping, say, an antenna, all right? And we're sweeping from 143 to 149 megahertz, all right? And we're going to find the minimum SWR point down here in this case, or the minimum return loss point, which is the same thing. Remember, SWR and return loss are the same thing. They're represented but merely by different numbers. And you can also see the reflection coefficient. But the reason that Smith chart view may not be reasonable to you or useful to you is because your VNA calculates all of this stuff anyway. You want to know what the input impedance of this thing is going to be. You put your cursor down here, and all right, here's log mag 10. This is return loss. All right, that's what they call return loss for some reason. It would be nice if they called it return loss, but log mag is 10 dB per division, and you can calculate it. Here's your reference point, this little thing over here, and you can 1, 2, 3, maybe 3.5, something like that at the cursor point. But here's the number, exactly 34.54 dB below the reference point. That is a really good, if you go back to that chart that I showed you before, it comes out to a really, really good SWR. Well, you don't have to go up to the chart because here it is. It's on the screen, 1.03 to 1, a really good SWR. And it's also shown here on the plot, and you can see it, all right? So whereas all of our previous discussions were talking about a single frequency, your VNA can do this as a sweep of frequencies, and you can move your cursor to any point on this line and get all of the information that you would normally get. Here's your input impedance, by the way, 48.2 minus J point. It's a little bit capacitive. And you can kind of see that it's a little bit below the line here at the point of the pointer. But it's really a pretty good, where I'm showing here, it's really a pretty good thing. And if you want to know what it is, that's a 48.2 ohm in series with a 2.05 nanofarad capacitor. Everything is here. This is an amazing graph. And it's an amazing amount of information that you have on your VNA just by doing the sweep. All of these numbers are alike. You have a VNA, and now you know it all. So the log mag is the return loss in dB. The SWR, you already know what that is. The Smith chart, yeah, okay. If you're really into Smith charts, you can use it. But there are no scales, but you don't really need scales because you just put your pointer on it and it reads all the information up here at the top. Now, Smith chart is really good for impedance matching problems, and I'm not going to get into that, but you can use it to do impedance matching. And this is really what it was designed for, and that's why it's interesting to know, but it may not be useful for you on your VNA. So, Matt asked me to add something here about maximum power transfer, and we're getting to the end here. But I think you know that maximum power transfer is when the load and the source resistance are equal, or in the case of complex loads and sources, when the load is the complex conjugate of the source resistance. I'm not going to go there, not going to really explain it, but you know, this is why we're trying to do this. We're trying to get our transmitter to put as much power into our antenna as possible. So it's important to know that even though you always see this, your source resistance is not necessarily 50 ohms. It's whatever the output impedance of your transmitter is, and it doesn't really matter. So you're trying to deliver as much power to the load as possible. So there's a difference between efficiency and maximum power transfer. They're not the same point, as you can kind of see. This is your efficiency curve. This is your maximum power curve. So what we're doing, I'm an amplifier designer, and when I did it is I tuned my amplifiers for maximum efficiency. That is power input divided by power output, maximum efficiency, current, voltage, and so forth. And all I didn't care about VSWR. I only cared about the return loss that is there. So I'm going to get into another two-port network here on the last two slides. And these are antenna tuners. They are nothing more than two-port networks that take one impedance and translates it into, well, ideally 50 ohms, so that your transmitter is happy. Now, the SWR on the line is still there, but it's merely masked by your antenna tuner, so that your transmitter, or my amplifier, if you will, is operating at maximum efficiency, not necessarily maximum power transfer. But you want it to operate at maximum efficiency so that you don't blow out the finals in your, whether they be tubes or transistors. Excuse me. Starting to lose my voice. And like I said, there's still VSWR on the line. But, you know, it's important to note here that the voltage peaks of the SWR are much higher than what would ordinarily be on a perfectly matched line. Whoop, I'm pointing the wrong graph again. The SWR peaks are much higher than on the perfectly matched line. And these voltage peaks can cause you problems. They can cause arcing, for example. Or if you recall, there's such a thing as current SWR, which kind of goes in here. And that current SWR has current peaks that are higher than normal. So the voltage peaks can cause dielectric losses, increased dielectric losses, and the current peaks can cause increased I squared R losses. So when you have VSWR on your line, your line actually has more loss than it does in a perfectly matched condition. Just so that you understand that. So what's the best place for your antenna tuner? It's right out here at the antenna. You don't have any SWR now, and you're really, actually, this becomes part of the antenna. You know, there's no such thing as a reflection in here, even though it sort of is, because you get all kinds of circulating currents going in here when in the impedance transformation. But the point is the SWR on the line is low, and you can keep the line losses at a minimum by putting your matching circuit out here. And a good example of matching circuits don't necessarily have to be antenna tuners, but they can be like the quarter wave open wire stub line on your G5RV, or it could be the coil that you place across the base of your vertical to raise the impedance. So the best place for it is out at the antenna, but the second best place is at the beginning. It's going to make your transmitter happy. Why? Because it can operate at the design point of 50 ohm load, and that's where the designer should have tweaked to maximum efficiency. So, final takeaway, if there's one thing that you got to take away from this entire presentation, is that you have an impedance meter, and measuring the impedance at the beginning of your transmission line can give you all the information you need about everything, about the antenna condition, about the return loss, about the SWR. And now that you have an impedance meter, you have all of the information it takes to understand your antenna. Use it as such, and everything else will become clear. So enjoy.